In this video, we're going to look at a legal problem called validate binary search tree. So given the root of a binary tree, determine if it is a valid binary search tree. So a valid binary search tree is defined as the following. So the left subtree of a node contains only nodes with keys that are less than node's key. The right subtree of nodes contains only nodes with keys that are greater than the node's key, right? So in this case, both left and right subtrees must be a binary search tree. So in this case, you can see, right, this is a valid binary search tree because the left subtree, all the nodes that are less than basically the current node's value or the current node's key. And the right subtrees are all nodes that has a key that's greater than the node's key, right? The root node's key, right? And same thing for its subtree as well, right? So you can see for this one as well. So in this case, for the left subtree, it should be less than, right? It should be greater than. The right subtree should be greater than the root node's value, but in this case, it's not the case, right? So therefore, this is false. And you can see we are guaranteed to have at least one node in our tree. And this is basically the node's values range, right? So in this video, I'm going to show you two approaches to solve this problem. One is we can use recursion to validate a range, right? We can set a range, this is the minimum, this is the maximum, and we use recursion to go from the top to bottom, right? And the other way we can solve this problem is we can be able to use Inorder traversal, which basically traverse the left subtree first. So we're visiting the values, so we're starting from the smallest value, and then we're visiting the current node, and then visiting the right subtree, right? So we're traversing the left subtree so that we're ensuring that we're starting from the smallest value, and we will have a previous pointer that keep track of the previous smallest value. So once we're going from small to big, right, we basically check to see if each and every single value is actually bigger than the previous value or the previous small value, right? Because we're going from small to big. So I'll show you two approaches. And then first, let's jump into the easy approach, which is basically recursion with range, right? What we can do to solve this problem is we can be able to set a range. So in this case, you can see for this binary search tree, right, we have node 5, node 1, node 4, node 3, and node 6. So what we can do initially is that because binary search tree, we have to ensure that each and every single node is at the correct position. What we can do is that we can see if this current node is within the correct range, right? So for the root node, in this case, we pretty much have negative infinity and positive infinity, right, as the range. This is our minimum, this is our maximum. So the thing is that when we want to validate the left subtree, right, or in this case, the remaining nodes, what we have to do is that if I want to validate the left subtree, I know the left subtrees, all the nodes that are in the left subtree are always less than node 5, always less than the root's value. So what we can do is that we can be able to set the minimum value still be negative infinity, but the maximum value, right, is basically going to be node 5, right? So in this case, what we do is that we ensure for each and every single node, right, the left subtree, the value should be within this range, right? So in this case, so let's say we have another value, for example, 0, right? In this case, same thing. So if I want to continue to do our DFS search down to go down, then the maximum value in this case is not going to be node 5 anymore. It's going to be node 1, right? The value 1, because the left subtree should always be less than the root's value. So the max is 1, and the minimum is negative infinity still, right? And same thing for the right subtree as well. For right subtree, the minimum should be 5. Right? Because all the values that are on the right subtree should always be bigger than the root's value. So in this case, the minimum is 5, and the maximum is basically positive infinity. So in this case, we ensure that for each and every single node, this is basically the range, right? It should not go beyond this range. So you can see node 4 is actually less than the minimum value. So therefore, this is not a valid binary search tree, right? So in this case, you can see we can just return false back to the root, right? So we basically pass down the min and the max, and as well as the current node's value, and then we validate it, right? So in this case, if a node is null, we can just return true, of course, right? But what's going to happen is that we're going to check the range, right? If the min does not equal to null, right? In this case, I put null here because you can see the range is that we have integer.max and integer, in this case, the positive infinity and positive, or in this case, integer.minimum value and integer.positive value. So node's value could equal to one of those two, right? So in this case, what we can do is we can just set null, right? In this case, what we can do is that if the min or the max is null, right? Pretty much, in this case, we don't have to check it. But if it's not null, then what we have to do is that we check to see if the current node's value, is smaller than or equal to the min, then we know that we basically go out of bound, right? In this case, this node is not at the correct range, right? In this case, this is not a valid binary search tree. So we return false. And then in this case, if the maximum does not equal to null, and the maximum is actually smaller than or equal to root's value, then we can also return false as well. So what's going to happen is that we're going to, once we validate the current node's position to see if the current node is at the correct range, we're going to validate the left side as well as the right side. At the end, we check to see if the left subtree and the right subtree are valid as well. If left subtree is not valid, we just return false, right? If the right subtree is not valid, we just return false for the right subtree, right? So basically, this is how we solve the problem. Complexity is big O of n, where n is number of nodes that we have in our tree. And the space complexity is going to be big O of h, where h is basically the height of the tree, right? We're using recursion stack. So in this case, the stack is basically the height of the tree. And there could be a situation where we have a linked list, right, kind of thing. Then in this case, we'll basically just traversing the entire nodes, right? So in this case, the space complexity will be big O of h, where h is basically the height of the tree. So now let's take a look at another way we can solve this problem. It's basically using a in-order traversal. So in this case, what we can do is, let's say we are still using this example right here, right? So in this case, we have node 5, and we have node 1, 4, 3, and 6, right? So what we can do is that we know the level, or in this case, in-order traversal is we traverse the left side first, then we visit the current node, then we visit the right side. So what we can do is that we visit the left side first, right? So what we do is that we traverse the left side. Once we traverse the left side, right, we're going to have a prev variable. This prev variable keep track of the previous smallest value, right? The previous value that we visited, right? So in this case, once we traverse the value node 1, right? In this case, this is the smallest value, right? So in this case, this is our leaf node. So in this case, the prev value will be node 1. And then what's going to happen is that when we go back to the root node, in this case, node 5, we know that the prev value is 1. So in this case, node 5, right, has a value of 5, which is bigger than the previous value. So it's valid. So it's good. So in this case, the prev is 5. So then once we traverse the left side and the current node, then we start to traverse the right side, right? So in this case, the next node is node 4. Then in this case, we want to traverse the left side first. So in this case, we visit node 3. Node 3 in this case has a value of 3, right? So in this case, 3 is not bigger than the pre-value. So therefore, we're just going to return false, right? So in this case, you can see here, what we do here is that we basically pass down the node's value, right? And just like in order traversal, we traverse the left side, then the current node, then the right side, right? So in this case, we do our base case. If the root is null, we just return true. And then we traverse the left side. So in this case, root.left, right? So once we visit a leaf node of the left side, right? So in this case, the very smallest value in our binary search tree, we check to see if left does not equal to, if it's false, right? If it's false, we can just return false, of course, so that we don't have to traverse the current node at the right side. And then what we do is that we visit the current node, right? So to visit the current node, there's a couple of situations here. So in this case, prev can be null, right? If prev is null, we can just say prev is equal to root.value, right? Because we haven't visited a node before, right? So in this case, we can just set, because we know the current node is the smallest value, so we can say prev is equal to root.val. And then if prev, right, which is the pre-value, is actually bigger than or equal to the root.value, right? So if 5 is bigger than 3, then we can just return false, right? Because in this case, this is not a valid binary search tree, right? So therefore, we just return false. Otherwise, you can see what we do is that we just basically set prev is equal to root.value. So there's pretty much three situations that could happen. One is the previous value is null, right, or negative infinity. So we just set the pre value equal to root.val, right? Otherwise, if the pre value is bigger than the current node's value, we just return false because it's not a valid binary search tree. Otherwise, if the pre value is less than the root's value, then in this case, we can continue to do our search, right? So in this case, prev is equal to root.val. So once that's done, once we visit the current node, then we just traverse the right side. So if the right side is give us false, then we're just returning false, right? Otherwise, if the left, the right, the current is all good, then we just return true, right? So pretty simple, and you can see the time complexity and space complexity will also be the same, right? So time complexity is big O of n, where n is the number of nodes that we have in our tree, and space complexity is going to be the height of the tree, right? We're using recursion, so in this case, the space complexity basically is stacks, right? So there you have it, and thank you for watching.